Good evening. Myself SNVSK Chaitanya, research scholar, MALO University. I am working as assistant professor in VR Siddhartha Engineering College, Vijayawada. My paper ID 5882. Title of the paper: Optimal Reactive Power Dispatch using Modified Antlion Optimizer with Fast Devices. These are the overview of my presentation. Optimal reactive power dispatch using with the modified Antlion algorithm and applied to IEEE 30-bus system without fax devices and with fax devices. The objective of the optimal reactive power dispatch are minimization of power losses and minimization of voltage deviation. The entire work running with the MATLAB programming. Optimal reactive power dispatch is a process of determining the most efficient allocation of the reactive power in a power system to enhancing the power performance. The goals of the ORPD is minimize the power losses, maintain the voltage stability, improve the overall grid efficiency and stability. The challenges in modern power system: rising the power demand, limit growth in generation and transmission due to the resource constraints, environmental regulations, and runaway problems. The techniques for solving the ORPD problem. So one is the mathematical programming. So traditional optimization methods, Newton-Raphson and Gauss-Seidel are some of the mathematical programs. Heuristic algorithms, the rule-based approach for finding the nearest optimal solution quickly for the complex problems, like genetic algorithms and partial swarm algorithms. Meta-heuristic algorithms, so techniques designed to efficiently explore large search space, balancing the exploration to find the nearest optimization solution. They are often inspired by the natural or biological process. So some of the examples are Grey Wolf Optimizer, Firefly algorithm, Antlion Optimization. Artificial intelligence also used for the particular solutions. So machine learning and fuzzy logic techniques are used for the particular purpose. These are the literature reviews papers for the optimal reactive power dispatch without fax devices, and these papers are with fax devices. So methodology: first develop the optimal optimization technique. Design and implement the modified Antlion algorithm for the enhancing the optimization efficiency. Application of the modified Antlion algorithm to ORPD. So apply the modified Antlion algorithm to optimize ORPD problem for the improve the power flow management. Control setting parameters: define and adjust the control parameters such as fax devices settings, switching capacitor banks, tap changing transformers, and generating voltage to optimize the performance. ORPD with the fax devices. Integrate the modified Antlion algorithm with ORPD to solve the power dispatch problems with utilize the fax devices for the system improvement. Solve the objective functions. Using the modified Antlion algorithm, calculate the objective functions like active power losses and voltage deviation, and apply this to the IEEE 30-bus system for the evaluation purpose. The paper work presents the meta-heuristic algorithm technique to solve the optimal reactive power dispatch problem with the fax devices. The objective functions are active power loss minimization, total voltage deviation, subjected to equality constraints like power balance and reactive power balance, inequality constraints such as generator constraints, reactive compensation sources, voltage limitations, and facts parameters limitations. This is the power loss minimization equation and voltage deviation minimization equations. These are the equality constraints, real power equation and reactive power equations, and these are the inequality constraints. So in the inequality constraints, voltage magnitude limits and tap settings of the transformer, real power limitations, and suitable VAR sources. So the values are adjust in between the minimum and maximum limits. So in this work, we consider the IEEE 30 bus system as the test system. So in the IEEE 30 bus system, 6 generators, 19 loads and 24 load buses and 41 transmission lines. In this IEEE 30 bus system, 19 control variables are needed to optimize which includes the 6 generator voltages and 4 transformers and 9 compensation devices. Generators are connected at a bus number 1, 2, 5, 8, 11, and 13. So these are the limits for the control parameters. Antlion optimization. Antlion is a meta-heuristic algorithm inspired by the behavior of the ant and antlion. It optimizes the problem by mimics the way ant interacts with the antlion gravitation pull. Antlions create a pit and trap the ant into a sand, symbolize the global best solution in the algorithm. Ants move towards the best solution, antlion, while also explore locally to find the better options. Antlion used this process to simulate the search and optimization. Modified antlion algorithm enhancing the antlion by better balance, explorate and explorate. This also a modified antlion algorithm to efficiently convergence towards the optimal solution in complex optimization problems. So these are the equations for the particular such value. Modified antlion algorithm, antlion optimization equation, and next one, modified antlion optimization equation. So in this equation, W is the variable. The value is varying with the varying in between the 0 to 2. Fact dividers. So fact dividers optimize the power in the transmission lines by adjusting the parameters like impedance and reactance, leading the reduce the overall losses and better assess utilization. Dynamic control of phase angle and voltage magnitude, enhancing the grid efficiency, enable more effective power delivery and future losses reduce. Due to the limitation on the building a new lines, electrical components must improve the techniques to maximize the power flow existing infrastructure. Power electronics based system that offer dynamic control of grid parameters to enhancing the optional flexibility. Fact devices can quickly injected or observe the reactive power, voltage levels, and maintaining the suitable voltage profile. So these are the objective functions with the including the fact dividers. So it is the equality constraints and inequality constraints. This is the model of the fax divergers. So STATCOM model, so where STATCOM is connected shunt at the bus. So PS is the active power at the shunt bus, and QS is the reactive power at a shunt bus. So Y-bus STATCOM is a modified Y-bus whenever we include the STATCOM. And similarly, it is a UPFC model. So UPFC is connected in the shunt and the series to the particular bus. And IPFC, so it is similar to the UPFC. So it is connected in between the two lines. So these are the voltage active power loss minimization table. So in this table represent the power loss minimization without fax divergers and with fax divergers. So we consider with the without fax divergers, the power loss minimization for the IEEE 30 bus system 4.1428 megawatts. In case of the STATCOM is connected across 23 bus, so the power loss minimized to 3.5821 megawatts. Similarly, UPFC, so it is connected to 23 and 24. The power loss is 2.9191 megawatts. In case of it is IPFC, so it is connected in between the two lines 412 and 413. The power loss minimization is 3.8033. So in the particular table, so UPFC gives a better result compared to the STATCOM and the IPFC. So the graph represent the figure represent the convergence characteristics of the different conditions. So in the x-axis, it represents the number of iterations, and y-axis it representing the power loss minimization. From the figure, we observe that the IPFC gives a better result and the convergence quickly. Similarly, so it is the table represents the voltage deviation with the different conditions. So without fax divergers, the power voltage deviation is 0.11936 per unit. In case we connected to the STATCOM at 18 bus, the power factor, the voltage deviation 0.0791 per unit. Similarly, UPFC is connected in between 18 and 19. So the power voltage deviation is 0.076 per unit. In case it is IPFC, 12.1216 and 1215 lines, the power voltage deviation is 0.0582. So in this table, we observe that the voltage deviation is also minimized at a value is low with the UPFC compared to the another fax divergers. And the figure represents the convergence characteristics of voltage deviation with the different conditions. So in the from this figure, we observe that UPFC gives the better voltage deviation and the convergence fastly. So in the x-axis, it is representing the number of iterations. In the system, in the work, we run 500 iterations, and Y-bus, it represents the voltage deviation in per unit values. The conclusion: the modified Antlion algorithm was developed to address the ORPD problem using the STATCOM, UPFC, IPFC fax divergers. The modified Antlion was tested on IEEE 30 bus system to reduce the active power losses and voltage deviation, comparing the result with the with and without fax divergers. Modified Antlion algorithm performs well across all ORPD objectives with the fax divergers. Power loss optimization was 3.5821 megawatts at STATCOM 2.9191 megawatts UPFC and 3.8033 megawatts in IPFC. Similarly, voltage deviation was minimized to 0.0791 per unit STATCOM, 0.076 per unit UPFC and 0.0852 per unit IPFC. UPFC produced a better result in minimization of power losses and voltage deviation compared to the STATCOM and IPFC. Modified Antlion algorithm combined with the UPFC produced the most effective and optimized ORPD objective. So these are the reference papers. Thank you.